Every light that flickers on, every city that glows at night, every train, hospital, and data center that hums with life, they all depend on one thing: the power transformer. Welcome to the supergiant power transformer factory, where thousands of tons of copper, steel, and silicon are turned into the beating hearts of the modern electrical grid. Before we dive in, don't forget to subscribe so you never miss a single journey into the world's most mind-blowing industries. The story of the power transformer began in the late 1800s, during the War of Currents. Thomas Edison pushed for direct current, while Nikola Tesla and George Westinghouse championed alternating current, a system that could travel long distances using transformers. In 1886, the first practical power transformers were built in the US. They were small, oil-cooled boxes compared to today's monsters, weighing over 400 tons and standing taller than a two-story house. From those early days, transformers evolved alongside America's growth, from rural electrification in the 1930s to today's renewable energy grid. And now, the country is witnessing a renaissance, new mega-factories rising to meet the surging demand for grid expansion and electric vehicle infrastructure. The process begins with cold-rolled grain-oriented steel, a special alloy designed to guide magnetic fields efficiently. Massive coils of this steel arrive by truck and rail, each weighing over 20 tons. In the cutting section, CNC shearing machines slice the steel into precise laminations, thin sheets that will form the magnetic core. Each piece must be cut with micrometer precision, because even a small gap can cause energy loss and overheating. Robotic arms then stack these laminations layer by layer, creating a magnetic loop, the core, where electricity will later be transformed from high voltage to low, or vice versa. The completed core can weigh up to 100 tons and is assembled using an interleaved step-lap design to minimize noise and maximize efficiency. If the core is the skeleton, then copper windings are the veins and arteries of a transformer. Kilometers of oxygen-free copper wire are drawn, annealed, and insulated before being wound around huge reels. These coils form the primary and secondary windings, where electromagnetic induction does its magic, stepping up or stepping down voltage. To prevent overheating, each winding is insulated using paper and Nomex layers, then baked in an oven to remove moisture. Robots assist in winding precision, but the alignment is still checked manually. One mistake can destroy an entire unit. Each giant coil can weigh several tons and must endure forces of over 100,000 newtons when current surges through it. Now comes the moment where steel and copper come together. In an assembly bay, the size of an airplane hangar, massive cranes lower the copper coils onto the magnetic core with millimeter precision. Technicians then connect the windings, bushings, and leads, following a schematic more complex than a rocket engine. Once assembled, the active part of the transformer is placed inside a steel tank, welded, reinforced, and leak-tested. It's then filled with mineral or synthetic insulating oil, which serves as coolant and dielectric barrier. Large radiators are attached to the sides, and fans are mounted to keep the oil circulating during operation. Each completed unit is like a mechanical cathedral, towering, humming, and gleaming with copper veins. Before any transformer leaves the factory, it must survive a brutal test phase. In high-voltage labs, engineers simulate lightning strikes, overloads, and sudden faults, pushing the machine to its limits. Arcs of electricity crackle across terminals as the voltage climbs to hundreds of kilovolts. Sensors measure heat, vibration, and magnetic flux to ensure nothing fails under real-world stress. It's loud, it's bright, it's pure power. Only the strongest transformers earn their certification to serve the grid for 40 to 60 years. After testing, the tank is drained, cleaned, and coated with anti-corrosive paint. Heat exchangers, oil pumps, and protective relays are installed. Next, the unit is refilled with ultra-pure insulating oil under vacuum conditions, removing every air bubble that could cause electrical discharge. Each component, from valves to gaskets, is double-checked. Nothing leaves this floor until it passes ISO-level quality inspections. By the end of the process, the transformer stands complete, often weighing more than 300 tons and valued at over $5 million. Transporting these beasts is an engineering feat on its own. Transformers are loaded onto multi-axle hydraulic trailers, often with more than 100 wheels, moving at walking speed through rural highways. Bridges are reinforced, traffic lights removed, and police escorts lead the convoy. Once at the substation, cranes lift the unit into place, and a team of technicians reconnects the components. When power finally flows through it for the first time, there's a deep, low hum. That sound is the heartbeat of civilization. In the age of clean energy, transformers are more important than ever. Solar farms, wind turbines, and battery storage systems all rely on transformers to stabilize voltage and deliver energy efficiently. American manufacturers are now developing eco-friendly transformers using biodegradable oils and 3D-printed components to reduce waste and improve cooling. Each innovation brings the grid closer to net zero emissions, and the factory floor is at the center of that revolution. From Witigi in Missouri to Hitachi Energy in Virginia and Siemens Energy in North Carolina, new investments are fueling America's return to industrial self-reliance. These factories are not just building transformers, they're rebuilding confidence in American engineering. Each steel tank, each copper coil, is a symbol of strength, resilience, and innovation. Because at the core of every megawatt flowing across the grid, there's a machine built by human hands, and a dream that still hums with power. If you love exploring how the world's biggest machines are made, hit that subscribe button, give this video a thumbs up, and stay tuned, because next time, we're going even bigger. They're taller than a man, heavier than a small car, and strong enough to carry hundreds of tons across the harshest terrains on Earth. These are giant mining truck tires. True engineering marvels standing over 4 meters tall and weighing more than 5,000 kilograms each. Today, we'll take you inside one of the world's largest tire plants, where heat, steel, and precision come together to build the monsters that move mountains. But before we begin, don't forget to subscribe, because we're about to roll into one of the most fascinating factories on Earth. Mining trucks are among the largest vehicles humans have ever built, some standing 2 stories tall and carrying up to 400 tons of rock in a single load. And without their massive tires, none of that would be possible. A single tire for these machines can cost over $40,000 and must survive extreme heat, pressure, and sharp rocks in mines across America, Australia, and South Africa. Unlike normal car tires, these giants are built almost entirely by hand, each layer crafted, measured, and molded with precision. In America's industrial heartland, one factory operates 24/7 to produce these enormous wheels. Here, thousands of tons of raw rubber, steel cords, and fabric are transformed into tires that can endure temperatures of 50 to 120 Faber and forces strong enough to crush steel beams. But how exactly do you make something this massive, yet perfectly balanced and reliable? Let's step inside the giant tire plant to see how the impossible becomes reality. Everything starts with natural and synthetic rubber, shipped in huge blocks from suppliers around the world. At the plant, these materials are mixed with carbon black, sulfur, and chemical agents in massive machines called Banbury mixers. Each one capable of kneading hundreds of kilograms of rubber at once. This process creates the base compounds: tread compound, designed for traction and durability; sidewall compound, for flexibility and resistance; inner liner compound, for air retention. Next comes the calendaring stage, where rubber sheets are combined with steel cords and textile fibers to create reinforced layers. These steel cords are what give the tire its internal strength, the ability to support the crushing weight of a mining truck loaded with hundreds of tons of ore. Every layer is precisely measured, down to 1/10 of a millimeter. Workers carefully align the steel belts, ensuring the tire will spin perfectly true, even at low revolutions, but under unimaginable pressure. In a world where one small defect could lead to catastrophic failure on site, quality control is everything. Lasers, sensors, and experienced eyes work together to ensure perfection before the tire even takes shape. This is where craftsmanship meets technology. Each tire begins as a green tire, an uncured structure made of multiple layers of rubber and steel, built on a huge rotating drum. Technicians stack the layers in a precise order: inner liner, body plies, bead bundles, sidewalls, and finally, the massive tread that grips the earth. Each component must align perfectly. Even a 1 millimeter offset could affect balance and cause uneven wear later on. Once the green tire is complete, it's lifted by cranes and carefully transported to the curing press. A giant steel mold that looks like something from a sci-fi movie. Inside, the tire is subjected to 200 degrees Celsius, 390 degrees Fahrenheit, and 350 psi of pressure for several hours. This is where the magic happens. Sulfur in the rubber bonds the molecules together in a process called vulcanization, giving the tire its toughness, elasticity, and final shape. When the mold opens, a perfectly formed 4-meter-tall tire emerges. Black, hot, and gleaming, it's cooled, inspected by hand, and then undergoes X-ray testing to ensure every internal layer is flawless. Each one of these giants takes more than 12 hours to build and costs thousands of dollars in labor and materials. But once complete, they're ready to conquer the toughest terrains on the planet. Before any tire leaves the factory, it faces a series of brutal tests. Giant machines spin and press them under simulated mining loads, equivalent to carrying 400 tons over jagged rock. Sensors measure heat buildup, sidewall flexibility, and even the sound of microfractures deep inside the rubber. Only those that meet exacting standards are approved. Defective ones are recycled, shredded and reused for new compounds, playground surfaces, or even road asphalt. Out in the field, these tires operate under extreme conditions. At open pit mines in Nevada and Arizona, temperatures swing from freezing cold to scorching heat. Each tire can last between 9 months to 2 years, depending on terrain and maintenance. When they wear out, Special tire handling machines, themselves costing millions, remove and replace them in minutes. Then the old tires are sent to recycling facilities, where they're cut, ground, and transformed again, giving new life to what was once industrial waste. The journey of a mining tire doesn't just end when it stops rolling, it continues in new forms, from construction materials to renewable energy systems. From raw rubber to 4-meter-tall engineering masterpieces, these tires are a symbol of human ingenuity and endurance. They move mountains, fuel progress, and keep the world's biggest machines rolling. If you enjoyed this deep dive into the giant tire plant, make sure to subscribe, like, and share. Because we're just getting started exploring how the world's biggest industries keep turning. Every day, beneath the soil of America, thousands of miles of steel pipelines quietly carry the lifeblood of modern civilization. Oil, gas, and even hydrogen. But have you ever wondered, how are these colossal steel tubes made? Today, we'll step inside one of the supergiant steel pipeline factories, where raw steel is transformed into massive, high-pressure line pipes that power the nation's energy grid. Before we dive deep into this industrial marvel, don't forget to subscribe and turn on the bell icon so you won't miss any new episodes exploring the world's most mind-blowing factories. The United States operates over 2.6 million miles of pipelines, enough to circle the Earth more than 100 times. From Alaska's frozen tundra to the refineries of the Gulf Coast, these steel arteries move crude oil, natural gas, water, and even captured carbon. But every mile of this vast system begins here, inside massive factories that specialize in line pipe steel. Unlike ordinary pipes, line pipes must withstand pressures exceeding 1,500 psi, endure freezing winters, scorching summers, and resist corrosion for decades. It's not just metal, it's engineered endurance. So how does America forge these steel giants? Let's start at the very beginning, with the raw steel itself. The process begins with high-strength steel slabs created from recycled scrap and iron ore at temperatures of 1,600 degrees Celsius. These slabs are reheated and fed through massive rolling mills, flattening them into wide, long sheets called hot-rolled coils, the backbone of every steel pipeline. Each coil can weigh more than 30 tons and stretch over 1 kilometer in length. Precision is key. Thickness variations must stay within 0.1 millimeter, or the pipe could fail under pressure. Engineers run constant ultrasonic checks, ensuring the grain structure of the steel is uniform and free from internal defects. Once cooled, these enormous coils are sent to the next stage, pipe forming. Here in the forming hall, precision machines bend the thick steel plate into a perfect cylinder. Depending on the diameter, factories use two main techniques: HFW, high-frequency welding, for smaller pipes up to 24 inches, DSAW, double-submerged arc welding, for extra-large pipes reaching 80 inches in diameter and 12 meters in length.